In today's video, we'll be discussing the action potential. After watching this video, you should be able to do the following 3 things. First, describe which channels are open during any stage of an action potential. Second, determine the membrane potential during any stage of an action potential given the relative conductances of the ions at that time. And finally, you should be able to understand the basis for the absolute and relative refractory periods. If you remember from the last video, you can use the Goldman equation to determine the membrane potential given relative conductances of potassium and sodium, as well as their equilibrium potentials. Okay? Remember again, in the real world you would also care about other ions like chloride, but in general sodium and potassium are the biggest drivers of membrane potential. So if we're recording membrane voltage from a cell, we have our electrode inside of our cell, so we're recording inside relative to outside. If that cell only had potassium channels, then that cell's equilibrium potential and membrane potential would be equal to the equilibrium potential of potassium, which as we have measured before is minus 60. So again, your electrode would measure minus 60 millivolts if all you had were potassium channels in that cell, which you don't. If all you had were sodium channels, then the equilibrium potential of that cell would equal that of sodium, or positive 60. But as we found in the last lecture, with a relative conductance of potassium of 9, sodium of 1, so way more potassium channels than sodium channels, your membrane potential at rest is closer to that of the equilibrium potential of potassium, or around minus 48 millivolts, what we had calculated last time. Now, remember, these are made-up numbers. They're fairly close to reality, but each individual neuron will have, depending on the species, will have a different resting membrane potential. Okay? Again, that's all driven by relative conductances for potassium and sodium, and you can use the Goldman equation to figure this out. If I suddenly opened a bunch of sodium channels, and so let's say I open enough so that the relative conductance of sodium is now 20 versus 1 for potassium, you would start to depolarize the membrane potential towards the equilibrium potential of sodium. Now we have more conductance for sodium. If I then close these channels and opened up a bunch more potassium channels, so now let's say that my relative conductance for potassium is 20 and for sodium is 1, that membrane potential would start to go down towards the equilibrium potential of potassium. And since, again, now there are way more potassium channels open than there are at rest, you would go even more hyperpolarized or more negative towards the equilibrium potential of potassium. Okay? If I then closed all those extra potassium channels and we went back to our resting membrane conductances of 9 for potassium and 1 for sodium, you'd be back at resting membrane potential. Now, this shape should look very, very familiar to you. This is an action potential. So we often talk of a couple phases of the action potential. The rising phase, when the membrane potential is going towards the equilibrium potential of sodium. The falling phase, when the membrane potential is falling back towards rest. And the hyperpolarization phase, or the undershoot phase, where the membrane potential is more negative than normal. I want to point out a few things. First, the time it takes to complete an action potential is on the order of 2 milliseconds or so. And second, as you can see, even though you've got way more potassium and sodium channels open at different points of the action potential, you will never ever hit the equilibrium potentials of sodium or potassium as long as there is still some conductance for the other ion. Okay? Remember, you can only be at that membrane potential if your entire conductance is going through the sodium or potassium channels. Action potentials have a threshold at which the all or none action potential will start. Okay? Usually that threshold is slightly more depolarized than rest, around 10 millivolts or so more depolarized. So in our case, let's say our threshold is minus 38 millivolts. if the membrane gets depolarized to minus 38 millivolts, you will get an action potential. Later in this video, we're going to talk about why there is a threshold and how the ion channels determine this threshold. We can look at the different ionic conductances and currents that happen during the time of an action potential. So here you have your membrane potential over time in the action potential, so there's just your action potential shape. If you look at the conductance of sodium over time, okay, you'll see that conductance peaks early during the action potential, right, during the rising phase, and then falls during the falling phase, whereas potassium conductance peaks later, okay, during the falling phase of the action potential. That all makes sense. That's just all what we've seen before. Now, we can also look at the current going through sodium or potassium channels over time. So current, as we know, is just voltage divided by resistance, or voltage times conductance, since conductance is 1 over resistance. So if we just want to look at sodium current, okay, the sodium current will equal the sodium conductance times what's known as the driving force. So the difference in voltage between the membrane voltage at that time and the equilibrium potential for sodium. Okay? Now, you're going to have a higher driving force when the voltage change is greater. So if you're further away from the membrane, if the membrane potential is further away from the equilibrium potential of sodium, there's going to be a higher driving force. So if we look at our sodium current trace in this graph, you'll see that the greatest amount of current happens again during the rising phase, and there's less current as you get to the end of the action potential. Now you'll notice a little notch there, and we're going to go into more detail for this in class, but basically you'll notice that at about that time your conductance has peaked, but you're very, very close at this point here to the equilibrium potential of sodium. So that means your driving force is going to be very low. Okay? So the more negative the membrane is, the higher the driving force, but then you also have changes in conductance for sodium over time. Okay? This is a little bit of a difficult concept, and that's why we're going to spend some time going over this in class. From the graphs that I just showed you, you can conclude 3 important points about how an action potential is generated. First, action potentials rely on changes in conductances. This means that channels must be opening and closing during the timescale of the action potential. Second, the change in sodium conductance graph looks the most like the membrane potential graph of an action potential. This means that changes in sodium conductance are the biggest drivers for the action potential. And third, sodium channels open and close faster than potassium channels. There are 4 main channels involved in generating the characteristic shape of the action potential. Your potassium and sodium leak channels, which we talked about before, and voltage-gated sodium and voltage-gated potassium channels. You'll notice that on this list, the sodium-potassium ATPase does not appear. The sodium-potassium pump is important for setting up concentration and electrical gradients, but over the couple millisecond timescale of an action potential, it does not play a major role. All of the ionic current, both sodium and potassium, is going to be flowing through the leak and voltage-gated channels. Okay, let's talk about when each of these channels are open. The potassium and sodium leak channels are open all the time. There's no gating involved, and as we talked about before, there are more potassium leak channels than sodium channels. The voltage-gated sodium channels are predominantly open during the rising phase of the action potential. They're gated by voltage, so when the membrane potential goes above threshold, they will open. Their regulation is fairly complex, and they have both an activation and inactivation gate, which we'll discuss in a minute. The voltage-gated potassium channels are also gated by voltage, so once the membrane goes above threshold, they will open, although they open more slowly. They're predominantly open during the falling phase and undershoot of the action potential. The voltage-gated sodium channel has 2 gates, an activation gate and an inactivation gate, which looks like a ball and chain. When the membrane is depolarized above threshold, the voltage-gated activation gate will open. Since the inactivation gate is also open, sodium can flow through the channel. About 1 to 2 milliseconds after that activation gate opens, the inactivation gate will close. This means that even though the activation gate is open, sodium ions cannot flow through the channel. When the membrane repolarizes, that activation gate closes again, and for 1 to 5 milliseconds or so, that inactivation gate will remain closed until it opens again, and now depolarizing the membrane can open and start the flow of sodium ions again. Okay, so the voltage-gated sodium channel opens quickly, but the inactivation closes within 1 to 2 milliseconds after opening. Okay, so that is why the voltage-gated sodium channel, we say, opens quickly and closes quickly, and why you see that narrow peak of the sodium conductance. It remains inactivated until after repolarization and at least 1 to 2 milliseconds has elapsed. This is very important for the refractory period that we'll talk about soon. The voltage-gated potassium channel is also gated by voltage, so once the membrane potential goes above threshold, it will open, and when it returns below threshold, it will close. So there's no inactivation gate on this channel. It just depends on membrane voltage. This channel, though, opens slowly and closes slowly. So once it goes above threshold, it takes at least a millisecond or so to open, and it will close a little bit after the membrane has been repolarized to rest. And that's what mediates the undershoot or hyperpolarization phase of the action potential. The properties of these voltage-gated ion channels determine the two types of refractory period. The first is the absolute refractory period. This is the period of time where the inactivation gate of the voltage-gated sodium channel is closed. So the millisecond or so after the peak of the action potential, where that inactivation gate is closed before it opens again following repolarization. During this time, another action potential cannot occur. No sodium ions can flow through the voltage-gated sodium channels when the inactivation gate is closed, which means you can't have the depolarization towards the sodium equilibrium potential. Now this is important so that you get discrete action potentials, right? If you had another action potential starting here, they could start to blur together. You don't want that. The relative refractory period is the time in which the membrane potential is more negative than rest. Another action potential can occur because by this time the inactivation gate of the voltage-gated sodium channel is open, but because those voltage-gated potassium channels are slow to close, membrane potential goes below rest, closer to the equilibrium potential of potassium, and it takes a larger stimulus to produce an action potential. Okay? During the relative refractory period, another action potential can occur, but it requires a larger stimulus. So what depolarizes the neuron to threshold? Experimentally, you can depolarize a neuron by injecting current, but in the body, most of the time, you use ligand-gated channels opened by neurotransmitters, which serve as the ligand, to allow positive current to flow in and depolarize the neuron. If you open channels that allows predominantly sodium current in, you can depolarize the neuron and get it to threshold, and then get those voltage-gated channels to open. If instead you open channels that hyperpolarize the neuron, for instance, that have mainly potassium flowing through them, you'll make it less likely that the neuron fires an action potential. We'll be talking about this in detail in the second portion of the class. Glutamate is the main excitatory neurotransmitter in the central nervous system. It opens cation channels that predominantly allow sodium to flow in, shown here. This then depolarizes the neuron, brings it to threshold, and you get those voltage-gated channels to open, and you get your all or none action potential. This concludes our action potential lecture. Remember, you should be able to do the following 3 things that we talked about at the beginning of the video, and you should be able to answer all the questions on the online test.